introduction to haloalkanes, and then we're going to look at some reactions that they can undergo. So we'll begin by saying that haloalkanes are substituted alkanes in which one or more of the hydrogen atoms has been replaced by halogen atoms. And the halogen atom can be treated like a branch when naming. So if we're naming haloalkanes, haloalkanes are named according to the IUPAC, that's the International Union of Pure and Applied Chemistry rules. That's, the rules that we've been using since National 5. And the presence of a halogen substituent or a branch is shown by the appropriate name. So if we've got a fluorine atom attached to our alkane, we would call it a fluoro branch. If we have a chlorine atom attached to our alkane, it's a chloro branch. If we have a bromine atom attached to our halogen, attached to our alkane, we would call it a bromo branch. And if we have an iodine atom attached to our alkane, it's an iodo branch. And haloalkanes with one hydrogen atom replaced by a halogen are known as monohaloalkanes. So of course that mono meaning one halogen. And haloalkanes with two hydrogen atoms replaced by two halogen atoms are known as dihaloalkanes, and so on and so forth. Now, the likelihood is with advanced earth chemistry, we will mostly be looking at monohaloalkanes. But let's just have a wee look at a couple of examples of haloalkanes so that we can see how their name relates to their structure. So our first one is 1-fluoro-2,3,3-trimethylbutane. So we're going to start by drawing this guy out. So anytime I am drawing pretty much any structure, I always start with the last part of the name because that tells me how many carbons I'm going to have in my longest chain. So it's butane, so that means there's going to be 4 carbons in the longest chain. And I'm always going to start by drawing 4 carbons in the longest chain. What I'm then going to want to do is number those carbon atoms just so that it makes things nice and easy. Now I'm just going to number left to right, just because that makes the most sense. So I've just numbered those carbon atoms. Then if I look at the next part of the name, I've got 2,3,3-trimethyl. Now that means I've got 3 methyl groups, which are CH3s. And the 2,3,3 tells me where each of those CH3 groups are. So I've got 1 on the second carbon, so I'm going to go ahead and put a CH3 on the second carbon. And then 3,3 means I've got branches on the third carbons, like so. And then onto the final part of the name, which is 1-fluoro. So that means that there is 1 fluorine atom on the first carbon. Okay, so that 1 tells you that it's on carbon number 1. Okay. If there were more than 1 fluorines, it would be like difluoro or trifluoro, so on and so forth, with a number indicating every carbon that a fluorine was attached to. And then all we have to do with this is to pop on the hydrogens to ensure that every carbon is making 4 bonds. So that will look like that. So that's your structure there for 1-fluoro-2,3,3-trimethylbutane. I'll give you just a little minute to give you some time to get that copied in. All right, so let's look at our second example. So this one is 2-bromo, 1-chloro, 2-methylbutane. So again, start with the last part of the name. That's butane, which tells you 4 carbon atoms in the longest chain. Then again, I'm going to go in and number those carbon atoms. And then I'm just going to continue working my way backwards with the name. So I've then got methyl, which tells me it's a CH3 branch, and that number 2 tells me that the CH3 is on the second carbon. So I'm going to go to the carbon that I've labelled number 2 and pop a CH3 there. I've then got 1-chloro, which means a chlorine atom on the first carbon. So I'm going to pop the symbol for chlorine, which is a capital C and a lowercase l, on that first carbon. And then got 2 bromo. So that's a bromine atom on the second carbon. So I'll pop that in there. And then again, it's just a case of making sure that every carbon is making 4 bonds by popping hydrogens on like so. All right, so again, I'll give you a moment just to make sure you've got that copied down. Okay, so in advanced higher chemistry, reactions of monohaloalkanes are the most common. So generally, those are the ones that we are going to look at, reactions of monohaloalkanes. So we're going to start by talking about types of monohaloalkanes. And this is going to be very much similar to looking at types of alcohols that we looked at in higher chemistry. So monohaloalkanes can be classified as primary, secondary, or tertiary, depending on the number of alkyl groups attached to the carbon atom which is bonded to the halogen. This is exactly the same as alcohols, except with alcohols, it's depending on the number of alkyl groups attached to the carbon atom that's bonded to the hydroxyl group rather than bonded to the halogen. Okay, so we're going to look at our 3 types of monohaloalkanes with a little diagram of each. Now we're going to keep these diagrams nice and general. So in the above diagrams, we're going to use the letter X to represent our halogen, and then R, R dash, and R dash dash to represent alkyl groups. Now, just as a reminder, alkyl groups are things like CH3, C2H5, C3H7. Any kind of carbon-hydrogen combination is generally going to be an alkyl group. Okay, so let's look at a primary monohaloalkane. So in a primary monohaloalkane, we'll have our carbon to our halogen, and that carbon is only going to be attached to a maximum of 1 other carbon, so 1 alkyl group. So I'm going to pop that alkyl group in there, but then the other atoms attached to that carbon must be hydrogens like so. So that's going to give you your primary monohaloalkane. For our secondary monohaloalkane, the carbon atom that's attached to the halogen is bonded to 2 alkyl groups. So those alkyl groups could be the same or they could be different. I'm just going to use R dash and R. They can be the same, they can be different. It really doesn't make any difference whatsoever. Okay, and then of course this carbon will be made to have 4 bonds with an additional hydrogen. So our final monohaloalkane is our tertiary monohaloalkane. So again, we're going to have our carbon to halogen bond, and then that carbon is going to be attached to 3 other alkyl groups, so it's not going to be bonded to any hydrogens at all. So it might look something like that. So again, I'll give you guys just a wee minute to make sure you've got those diagrams copied in. Okay, so we're going to come back to looking at why types of monohaloalkane are important a little bit later on. Okay, so we're just going to kind of leave that hanging in the background. So we're going to go on to look at reactions of haloalkanes. So haloalkanes will undergo two main reactions. An elimination reaction that we've actually already looked at when we looked at alkenes, and a nucleophilic substitution reaction. Now, nucleophilic substitution reactions are brand new, and we will be looking at them in as much detail as we looked at addition reactions for alkenes, so we talk about them a lot. Okay, so we're going to start with a little recap of elimination reactions. So as discussed in preparation of alkenes, monohaloalkanes will undergo elimination reactions when they are heated under reflux with ethanolic potassium hydroxide or ethanolic sodium hydroxide. Okay, so we would call this a base-induced elimination, and that kind of name base-induced tells you that you're going to use a base to do the reaction, because potassium hydroxide and sodium hydroxide are both bases, and we must dissolve them in ethanol rather than water. Okay, and we'll see why we dissolve them in ethanol rather than water a little bit later on. Okay, so let's look at the couple of examples that we've got here. So base-induced elimination of chloroethane. So the first thing I'm going to do is draw chloroethane out. Right, so there's my chloroethane. And we're going to draw our reaction arrow. And on top of that reaction arrow, I'm going to pop my potassium hydroxide, KOH, and then indicate that it is dissolved in ethanol by putting the word ethanol in brackets after the KOH. Now, what will happen is that will cause the halogen atom to be removed and also a hydrogen from the carbon next door. So any one of these three hydrogens could be removed as well. So I'll go with that one there, okay? So what that will do is it's removing two atoms. So we'll draw what we would have if we removed those two atoms. So we've got something that looks like this. Now the problem is both of those carbons are only making 3 bonds when they both need to make 4. So what we do is we get a carbon-to-carbon double bond that forms in between those two carbon atoms just to make sure that they've all got 4 bonds. So an elimination reaction of a haloalkane will make an alkene. And then our other product would just be HCl. So just the 2 atoms that have been eliminated, like so. Okay. So again, I'll just give you a moment on that, and then we'll look at our second example. Okay, so our second example is just going to remind us that depending on the haloalkane, we can actually get more than one alkene forming in this reaction if we have a haloalkane that, you know, makes that so. So if we look at the base-induced elimination of 2-fluorobutane, we can see exactly how that can transpire. So I'm going to start drawing my diagram for 2-fluorobutane down a bit, because what we're going to do is we're going to split our reaction arrow into 2 so that we can see the 2 products that are going to form in this reaction. So I'll draw my 2-fluorobutane out, popping my fluorine atom on the second carbon. Like so. Again, with my reaction arrow, I am going to use my base. Now for this one, I'll just use sodium hydroxide just for a wee bit of variety, but potassium hydroxide would work absolutely fine. Again, we need to dissolve that in ethanol. And for this one, we're going to look at the kind of 2 different ways in which we can do our elimination. And what I'll do is I'll color code the arrows. So we can choose to remove the fluorine atom and the hydrogen on the left-hand molecule, or we could choose to remove the fluorine atom and then the hydrogen on the carbon to the right. And what that will end up doing is it'll cause the double bond to form between two different carbons, which will give us two different alkenes. So if we look at this first one here, so what I've done is I have removed the hydrogen and the fluorine. And I need to pop the carbon-to-carbon double bond that is going to form in between those two carbons that have lost the atom each. And that will produce but1-ene as our product there. And then the alternative is to still remove the fluorine from the second carbon, but for this one we're removing the hydrogen from the third carbon rather than the first carbon. And this time we would form the carbon-to-carbon double bond in between the second and the third carbon, which would give us but2-ene as our product. So again, I'll give you a little minute or so just to make sure that you've got a wee bit of time to copy those diagrams in. Okay, so that's just a wee bit of revision from the work that we done at the beginning on how we can prepare alkenes. So what we're now going to do is look at another way in which we can react monohaloalkanes, and that is with a nucleophilic substitution reaction. So looking at nucleophilic substitution reactions. So monohaloalkanes will undergo nucleophilic substitution reactions with 3 different reactants, forming 3 different products, okay? And we have to know about all of them. So we can use an aqueous alkali to form an alcohol. We can use an alcoholic alkoxide to form an ether. And we can use ethanolic potassium or sodium cyanide to produce nitriles. Okay, so that's 3 different products that we can get from a monohaloalkane. So monohaloalkanes in organic chemistry are really, really useful because we can get 3 different products from it. So if you've got a monohaloalkane, you could turn it into an alcohol, you can turn it into an ether, you can turn it into a nitrile. So really, really useful. Whereas there are some reactants that can maybe only undergo one type of reaction. Monohaloalkanes can undergo 3 different nucleophilic substitution reactions. So the carbon to hydrogen bond in a monohaloalkane is a polar covalent bond. The hydrogen atom has a greater electronegativity value, so a greater attraction for bonded electrons, and that will pull the electrons in the bond closer to it, creating a partial negative charge on the halogen atom and a partial positive charge on the carbon atom. So what that would look like is you would have your carbon to your halogen. Again, I'm just using the symbol X for a halogen. Now, every halogen has a greater electronegativity than carbon. The difference in electronegativity values will, of course, vary depending on what the halogen is, but every halogen atom that we use in these reactions has a greater electronegativity than carbon. So the halogen atom will always be delta negative, and then our carbon atom will always be delta positive. And I've just popped 3 other bonds on that carbon atom because, of course, carbon does make 4 bonds, so you wouldn't just have that bond completely on its own. The carbon would be attached to other substances. And the partial positive charge on the carbon atom makes it susceptible to attack from nucleophiles. And it is for that reason that monohaloalkanes can undergo nucleophilic substitution. If we didn't have that difference in electronegativity value, the carbon wouldn't have a slightly positive charge and the nucleophiles would have nothing to attack. Therefore, the reaction simply wouldn't happen. Right, so we'll look at our 3 different nucleophilic substitution reactions forming our 3 different products. So our first one is a nucleophilic substitution forming alcohols. So we're going to look at a nucleophilic substitution of 1-chlorobutane. Now, what I'm going to do in each of these examples is I am going to color code the nucleophiles in blue so that we know exactly what the nucleophile actually is in every one of these reactions. It's always going to be the substance that's got a negative charge or electrons in a pi bond, so like anything that's got a carbon-to-carbon double bond, or even neutral molecules that have got 1 or more lone pairs of electrons. But just to make it a wee bit easier, I'll color code them in blue so that we know exactly what the nucleophile is. So I'm going to start by drawing 1-chlorobutane out. Now, in our nucleophilic substitution reactions, what will happen is the halogen atom will be substituted for the nucleophile. So whatever our nucleophile is going to be drawn in that green highlighted area, and the chlorine is going to come off. So it's just a straight swap, it's a straight substitution. All right, so when we form an alcohol using a monohaloalkane, we must use an alkali like potassium hydroxide or sodium hydroxide that has been dissolved in water. Okay, now in this reaction here, the hydroxide ions, the OH minus ions in the alkali, they are our nucleophile. So that's why I've popped them in blue. So what will happen is the chlorine atom will be removed from the butane chain. And the nucleophile will take its place. And the potassium in the alkali will combine with the chlorine that has been removed. And what we've got as our product is butan 1-ol. So that's our nucleophilic substitution to form our alcohol. And this reaction is carried out with aqueous sodium hydroxide or aqueous potassium hydroxide. You do need to know what reagents you need to use in order to turn a monohaloalkane into an alcohol, instead of turning a monohaloalkane into an ether, or a monohaloalkane into a nitrile, or even turning a monohaloalkane into an alkene. Because if we were to use an alkali like potassium hydroxide that was dissolved in ethanol, what would happen is we would produce an alkene. And I'm just going to quickly scroll up just to remind you of that there. So you can see here that for this reaction here, we're using potassium hydroxide that's been dissolved in ethanol. And rather than getting a substitution reaction, what we get is an elimination reaction. So the reagent is very important, and also what we dissolve the reagent in is very important as well. And the difference between dissolving potassium hydroxide in ethanol versus water is the difference between turning your monohaloalkane into an alkene or into an alcohol. So you get very different products there. Okay. So that's our little example of how we can form an alcohol. Okay. Now, we're going to go on to talk about nucleophilic substitution forming ethers. Now, there's a wee bit more to a nucleophilic substitution reaction when we form an ether. Now, it says before nucleophilic substitution to form ethers can take place, it is first necessary to produce an alk oxide. Now, an alk oxide is what our nucleophile is going to be. So basically, we need to produce the nucleophile. All right. Alk oxides are negatively charged ions in which an alkyl group is bonded to an oxygen atom. Okay, so alk oxides are negatively charged ions in which an alkyl group is bonded to an oxygen atom. Guess we could actually probably change that to oxygen ion. It's probably a wee bit more descriptive. So I'm just going to draw in a little example. So we could take an alkyl group. So for example, we might have like a CH3 and it's bonded to an oxygen ion like that. Or we might have like a C2H5 and it's bonded to an oxygen ion like so. Okay, so those are our alk oxides. Now an alk oxide is produced by dissolving an alkali metal in an alcohol. Now, that is a very, very small part of the advanced higher course. However, I would say it gets asked in close to 50% of exam papers. How do you produce an alk oxide? Things like that. So there are lots of questions on producing alk oxides, sometimes in multiple choice, sometimes in your short answer questions. So it is absolutely well worth knowing and remembering that piece of information. So our table just shows how we can use different alkali metals and different alcohols to produce different alk oxides. So if we use potassium and methanol, we would get potassium methoxide. And that methoxide, that's our nucleophile. And what I'm also going to do is I'm just going to pop the formula for potassium methoxide just at the side. So potassium methoxide would be K plus for our potassium ion. And then methoxide is a methyl group attached to an oxide. So I'm going to pop in my O negative and then put my methyl group on that there. And it's that bit there, the bit in blue, that's your nucleophile. So that's the bit that's going to substitute onto your molecule. If we react sodium with methanol, we get sodium methoxide. So that would be Na plus. And then our methoxide ion. We don't just need to use methanol, we can use other alcohols. So if we react potassium with ethanol, we'd get potassium ethoxide. So that's going to change the alk oxide. So it's going to be K plus, then we're going to have our oxide ion, and then it's going to have an ethyl group on it, a C2H5, like so. And then that O minus C2H5, that's going to be your nucleophile. And then finally, if we use sodium and react it with propan-1-ol, we'll get sodium propoxide. So if we look at sodium propoxide, it's going to be Na plus, oxide ion, and then a propyl group is a C3H7. And again, that's going to be your nucleophile there. So the alkoxide dissolved in alcohol is then used in the production of ethers. So we're going to look at example 1, which is nucleophilic substitution of bromopropane with sodium ethoxide in ethanol. So your nucleophile here is going to be the ethoxide. So let's have a wee look at this reaction. A wee bit of a typo here. We're going to make that 1 bromopropane. It's just missing the number and the letters were back to front. Okay, so let's start by drawing out 1 bromopropane. Right, so there's my 1 bromopropane. And in order to turn this into an ether, I am going to use sodium ethoxide dissolved in ethanol. So that's going to be Na plus. Then I'm going to keep my nucleophile in blue. And it's going to be OC2H5. And then just making sure that I indicate that that's dissolved in an alcohol. It wouldn't be dissolved in water. Okay, because dissolving it in water would mean that we might get a mixture of products being produced, because what water contains H plus ions and OH minus ions. So water actually has a little supply of nucleophiles in it. So if you dissolve the sodium ethoxide in water, some of the hydroxide ions that are present in the water would do the substitution reaction instead of the ethoxide. And then that would give you a mixture of products. So it would give you a mixture of alcohols and ethers. And generally, when we are doing reactions in chemistry, we want to avoid mixtures of products as much as possible, because it costs money to separate products from each other. So it would cost money to separate the alcohol from the ether. So we want to avoid that. And the way we avoid that is by dissolving the ethoxide in ethanol, because that makes sure that there's no hydroxide ions that could do the substitution instead. So I'm just going to redraw everything with the exception of the halogen, because the halogen is what is being substituted. Now, what is going to happen here is we are going to substitute on our ethoxide. So we're going to pop in a bond to the oxygen, and then that oxygen is bonded to a C2H5. So I'm just going to draw that out as a full structure rather than just writing it as C2H5. And what we have drawn here is our ether. So ethers are molecules in which you've got an oxygen atom that's surrounded, or that has alkyl groups on each side. So you can see on the right hand side we've got a C2H5, and on the left hand side we've got a C3H7. That's what an ether is. We've got a full lesson that we'll be doing on ethers a little bit later on, including looking at naming them and looking at their properties and so on and so forth. But for just now, we can kind of just get away with knowing roughly what an ether is. Okay, and that's your ether there. And then by producing different alkoxides, it is possible to produce different ethers. Okay, so what I'm going to do is I'm just going to name the ether that we have produced just now, because it will make sense once we've come to the end of the synthesis topic and when you're looking back over your notes. So this ether is called ethoxypropane. And there are probably hundreds of different ethers that we can produce. And if we used a different alkoxide, we would have produced a different ether. We wouldn't have produced ethoxypropane. We might have produced methoxypropane or propoxypropane or butoxypropane, any number of different ethers. Okay, so what we're going to do now is we're going to look at a second example of reacting another haloalkane with a different alkoxide and producing a different ether. Now, memory serves me, this one actually produces the same ether. So what we're going to do is we're going to change chloroethane to chloromethane just so that we actually get a different ether, because it doesn't really make any sense to talk about getting a different ether and then using two substances that end up giving you the same ether as the one previously. So we'll use chloromethane for this. So we're going to use chloromethane with potassium propoxide that's been dissolved in propanol. So again, I'm going to start by drawing out my chloromethane. So that's just going to be methane, but with a chlorine atom in place of one of my hydrogens. I am then going to react this with potassium propoxide. So that's going to be K plus, and then the propoxide is my nucleophile, and that's going to be OC3H7. And then that's going to be dissolved in propanol. It generally makes sense to dissolve your alkoxide in the alcohol that you use to make it. So if you've got propoxide, then it was made by reacting with propanol. So use propanol to dissolve it. So if you match the number of carbons in your alkoxide to the number of carbons in your alcohol, then you're not going to go far wrong. Right, so when we look at our product here, we're going to remove the chlorine, and in its place we are going to substitute our nucleophile. Now the nucleophile here is quite large. You know, it's an oxygen with 3 carbon atoms attached to it, so it's fairly sizable. So when we're substituting, we don't just need to substitute like one atom for another atom or even like 2 atoms. We can do quite a large substitution, and that has given us a different ether. Now in this reaction, the potassium and the chlorine will just come together. So we'll pop in plus KCl. And we will call this one methoxypropane. So it's still an ether. It's just a different ether from the one in example 1. So we've got ethoxypropane and we've got methoxypropane. So 2 different ethers there. They don't have to end in propane. We could have methoxymethane, we could have methoxyethane. Just so happens that these ones are propanes. Okay. Right, so again, I'll just pop the page onto those 2 diagrams and give you a wee moment to make sure that you've got them copied in before going on to look at the third way in which we can react our haloalkanes. All right, so let's look at that third type of nucleophilic substitution, which was to form a nitrile. Okay. So going on to look at nucleophilic substitution forming nitriles. So we're just going to begin with a little introduction, which says that nitriles are compounds that contain a carbon to nitrogen triple bond. Now, the importance of this reaction in organic chemistry cannot be understated. It is the only reaction in advanced higher organic chemistry that can increase the number of carbon atoms in a chain. Now that's really, really important. So for example, if you were working in industry and you worked producing different products for different companies, and you had a company that came to you and said, I would like you to make me propanoic acid. If the starting materials that you have are things like chloroethane, then what you would have to do is do a nucleophilic substitution in which you turn the eth, 2 carbon atoms in your chain, into a prop, which is 3 carbon atoms in the chain. And this is literally the only way in which we can do that. So if you're starting with 1 fluoropropane and you want to end up with butanol, then it has to go through this, because that's the only way you can increase those number of carbon atoms in your longest chain. So it's quite distinctive if you remember that fact there. So this reaction is carried out with ethanolic potassium cyanide, which is KCN dissolved in ethanol, or ethanolic sodium cyanide. And our nucleophile in these reactions are going to be the cyanides, because cyanides is a negatively charged ion, so that's going to be our nucleophile. And again, we are looking at dissolving in ethanol, not in water, because if we dissolve in water, there's hydroxide ions that are present. Those are also nucleophiles, and then we can end up with a mixture of products, which we are trying to avoid. So I'm going to look at 2 little examples here. So this first one is a nucleophilic substitution of bromoethane. So I'm going to start just by drawing out my bromoethane. Like so. And again, I'm going to pop in my reagent. So I'm going to use, let's use potassium cyanide. So potassium cyanide is ionic. It's got a metal bonded to non-metals, so generally those are ionic, although of course there are some exceptions. The nucleophile is the cyanide, which is why I've popped that in blue, just keeping that habit up and dissolving that in ethanol. So what we're going to do here is we are just going to do a straight substitution. So the bromine is going to come off, and we are adding that carbon to nitrogen triple bond. And what I'm going to do is I'm just going to number the carbon atoms in the longest chain so we can see that it's increased. So in our reactant here, we've got 2 carbons in our longest chain, and then in our product here, we have 3 carbon atoms in our longest chain. Again, I'll just give you a moment to make sure you've got that copied in. All right, and then we'll look at another example, which is going to be our nucleophilic substitution of 1-fluoropropane. So we'll take our 1-fluoropropane, like so. For this one, I'll use sodium cyanide in ethanol, just to be a little bit different. But again, you could use potassium cyanide in ethanol and it would work absolutely the same. And what is going to happen here is, again, that fluorine is going to be substituted with the C triple bond N. And again, what we're going to see is our number of carbons in the longest chain has increased from 3 to 4. Okay. Now, in terms of what we can then do if we've made a nitrile, is nitriles, in terms of advanced higher chemistry, only undergo one reaction. And we convert the nitrile group into a carboxyl group by an acid catalyzed hydrolysis. Okay, so acid catalyzed hydrolysis, again, a very small part of the course, but a part of the course that we really, really, really need to know. So I'm going to just show you what that would look like. So I'm going to just take the nitrile that we made in the reaction in example 2, just because it's there and we can see it nice and easily. So it's an acid catalyzed hydrolysis. So acids all contain H plus ions. So anytime something is acid catalyzed, we're wanting H plus ions, and hydrolysis means it's been reacted with water. So it's going to be water and H plus ions that are our reactants there. And what will happen is we will break that carbon to nitrogen triple bond and replace it with a carboxyl group like so. And then our other product is going to be an ammonium ion. We really don't need to bother too much about the other product at all. The key thing is we are getting our carboxylic acid, and we could actually go ahead and name that one. That's butanoic acid. So breaking that carbon to nitrogen triple bond and replacing it with a carboxyl group. So a C double bond OH on that same carbon. And then once we've got that carboxylic acid, we can then react that in numerous different ways. There are so many things we can do with a carboxylic acid. So I'm just going to list a couple of them here. So we can do a reduction to form an aldehyde or alcohol. We could do a condensation to form an ester or an amide. We could do a neutralization reaction, because it is an acid after all, to form a carboxylate salt. So once you've got to a carboxylic acid, there's loads and loads of different things that we can then do in terms of reacting that carboxylic acid. And the key thing is we have increased the number of carbon atoms in our chain by doing the nucleophilic substitution to form that nitrile. Nitriles themselves, not particularly useful. We can really only do one reaction with them, and that's your acid catalyzed hydrolysis. Okay, so again, I'll give you a couple minutes just to make sure you've got that information in. All right, so that's all of the different ways or all of the different products that we can get when we do a nucleophilic substitution reaction. But unfortunately, it's not enough to just know that we can use a nucleophilic substitution reaction to turn a monohaloalkane into an alcohol, into an ether, into a nitrile. We need to go in to look at the mechanism behind how the nucleophilic substitution reactions work. And unfortunately, that means more curly arrow diagrams. So we're going to do like a little introduction to looking at these mechanisms.